Okay, so I left you with these two pictures of the Orion Nebula, optical on the left, radio on the right, and asked you to think about the differences between them or have a discussion about them. So I think the main obvious difference is that there's this kind of dark patch here encroaching on the nebula on the left, which is not really visible on the radio image. Similarly here, there's sort of dark patches. So this is really to do with dust extinctions, the little interstellar dust grains that are mixed in with the gas that are blocking the view of the nebula light behind here. So this is don't forget, it's a three-dimensional object in the sky. And so there are some dust clouds just creeping around the front here of the nebula. And this is one of the key advantages of radio waves, is that they see right through any interstellar dust clouds. You don't have any extinction effects at all. So again, you get a much clearer view of the bubble of gas here. And we'll see examples later where you just simply can't see the nebula in the optical at all. Other minor differences you might see, of course, are that there are some stars here. Certainly that one. That is was clearly not present at all here in the radio image. And basically most radio images most stars do not show up in radio images because they have very little or no radio emission. Okay, so let's now look at why these sources are emitting in the radio and how, and learn a few more things about that. So HII regions, as I said, are very strong radio continuum emitters, and they are emitting in the radio because of this thermal free mechanism or bremsstrahlung. Okay, so this is the idea of an electron that comes along and gets accelerated by an interaction with a positive nucleus. So normally the proton, if you've just got hydrogen gas. So an electron accelerated around the proton just electrostatically, the attraction of the negative particle to the positive nucleus. And any accelerated charge will emit photons. Okay, so as it's bent around, it starts to emit photons. The more it's bent, the tighter the radius of curvature, the higher the energy of the photon, or the shorter the wavelength. Okay. So I'm just going to flesh this out a little bit and bring in some of the concepts that we just learned about in the radiative transfer lecture. So the atomic physics here it is quite complicated. So you may have learned in physics what the emission properties of a charge being accelerated at a particular rate is. And so obviously as it moves around here, then the rate of acceleration is going to change, and so therefore the wavelength of the light will change. Also, depending on how close the encounter is, this will all be different. Okay, and depending on the speed at which the encounter occurs is also different. So to arrive at the amount of emission or absorption due to these processes, you need to take into account all of those different parameters. So that's very involved, and we're not going to go through that. But just to see what the dependencies on the different variables are and to understand them, then we can see on the top of here that the opacity is dependent on both the number density of the ions here. So previously, if we were just thinking about hydrogen, this would be NP again, but here I'm replacing it with Ni. There might be other, you've got 25% of the gas is helium rather than hydrogen in reality. So, normally you need to take account of that. And obviously the number density of the electrons again here. So again, two-body process, so it's proportional to the number density of both. If you have more of either, you're going to get more opacity. So that's fairly obvious. The fact that there is a temperature dependence here is because of what I just mentioned about you need to take into account the speed of the electrons. okay? And so that means you've got to sort of integrate over the whole Maxwellian distribution of electron velocities at a given temperature, okay? So the temperature will determine the Maxwellian distribution of velocities, and so therefore there's clearly going to be a temperature dependence. If you've got hotter gas, then the chances of getting the encounters basically just drops, really. And so that's why it's inversely proportional, approximately. Certainly at a given frequency, anyway. Okay, and the frequency dependence is proportional to nu to the around about the minus 2.1. Okay, so this is kind of approximate. And again, so you're going to have more encounters at larger distances from the nucleus on average. So it'd be rare to have an encounter near the nucleus. And so therefore, the encounters further away from the nucleus give rise to more low frequency interactions, low frequency photons. So therefore, you get this dependence. So I just want to now explore, I just subtly changed from opacity to optical depth here. So this was the opacity formula. But of course, optical depth is just this times some path length. And so that it will have the same frequency dependence. Okay, so the optical depth at a particular frequency depends on nu to the minus 2.1. So that means as we go to lower and lower frequencies, the opacity gets higher and higher quite quickly. Okay. So recall from the radiative transfer lecture that in an optically thick situation, if the optical depth is greater than 1, the intensity is basically just given by the Planck function if we are in thermal equilibrium, which for these kind of nebulae we are as far as the radio process is concerned. So, and again, recall that at radio wavelengths, at low frequencies, then and all radio wavelengths, this Rayleigh-Jeans approximation is fine for the Planck function. So you can see here that the frequency dependence is just nu squared. Okay. All of the rest will be constant if the temperature stays the same at around about 10,000 Kelvin. Okay. What happens if we go to the optically thin end? So that will occur at higher frequencies. At some point, the optical depth will drop below 1. So recall then that the intensity would be given by the Planck function times the optical depth. Okay. So if we look at the frequency dependence of that, we've still got the nu squared dependence coming from the Planck function, b nu, but we've got a nu to the minus 2.1 coming in from the optical depth. So if you multiply those two things together, you just need to, add up the exponents, and that's going to give us a nu to the minus 0.1 dependence for the intensity. So almost independent of intensity, of frequency at nu to the minus 0.1. And if we look at the spectrum of the Orion Nebula, the nebula we were just looking at in the radio, then you see this. This is very characteristic so-called spectral energy distribution, or SED. So a spectral energy distribution is basically like a continuum spectrum, and you'll see this for a variety of sources throughout this course. Again, this, try not to be confused, this S nu here has nothing to do with the source function. This is basically radio flux. Okay, so this is the radio flux as a function of frequency. So it's a bit like the intensity in this case. And we can see that here at high frequencies, okay, so this is 1,000 megahertz or 1 gigahertz, this is 10 gigahertz. So up here at 10 gigahertz, we can see that the intensity of the radio waves basically stays nearly constant. It's just dropping down a little bit, and that is the nu to the minus 0.1 dependence that we just looked at for optically thin emission. If we go to lower and lower frequencies, so down here at like 100 megahertz, we can see that the spectrum starts to fall off rapidly as we go to lower frequencies. And so this is S nu is proportional to nu squared here, okay, so that the intensity is rising with frequency as nu squared, going this way. And somewhere in the middle where the spectrum turns over, we know that basically the optical depth will be 1, okay. And so that's, yeah. So by looking at the characteristics of this spectrum and understanding the opacity and the optical depth, we can actually derive some of the physical properties, especially the sort of densities and that kind of thing as well. Okay, so again, we'll be sort of looking into that in the workshop later on. So we can see that, again, I mentioned this in the introduction, that this idea of a spectral index is very useful. So a spectral index is the slope of the radio continuum spectrum, okay? And well, galactic astronomers, at least, or usually use this format, that S nu is proportional to nu to the alpha. And so this is the slope in a logarithmic, or the gradient of the line. Alpha would be the gradient of the line in a plot of log S nu, where this is flux against log frequency. And you can see that both of these axes are logarithmic, which is why we're getting a straight line power law here and a straight line power law here. Okay, so it's a log-log plot. And again, that's very common for spectral energy distributions. And you look at the slope of the curve, the gradient of the lines, to give you the power law exponent. So in an ideal constant density H2 regions, alpha would be minus 0.1 when it's optically thin and plus 2 when it's optically thick. Okay, so by measuring the radio spectrum at different frequencies, you can work out whether you're optically thick or thin, and then you can use the right formulae accordingly to try and derive physical parameters for your object. So just a word of caution that when my extragalactic colleagues, so people who study radio emission from other galaxies, come to lecture you, they might well start talking about spectral index, but they might have the opposite definition, okay, where you've got a negative sign there, in which case all of these switch sign, but we'll worry about that when we get there. Okay, so those are some basic radio properties and some formalisms that describe the radio properties of H2 regions. Let's just think a little bit about what happens to these H2 regions once you've started them ionizing their gas. Over time, as I indicated earlier, they kind of start to expand and break out of the cloud that they were started to form in. And this, why do they expand? Because basically they've just got a higher pressure than their surroundings. And this is just mainly thermal gas pressure. So I just want to recap here. So again, hopefully most of you have seen this equation before, which you would have learnt at sort of high school physics for pressure of gases, the ideal gas law, PV equals nRT, where N is the number of moles of gas and R is the universal gas constant and T is the temperature, P pressure and V the volume. So in astrophysics, we usually turn this around and you can see that if we make P the subject here, you end up with N, this is number of moles divided by volume. But that's basically a number density. So it's characterizing the number of particles per volume. And so that is number density. So for astronomers, we would use this little n here as number density and say that the pressure is proportional to the number density times the temperature. Okay. So if we just go and look at the conditions inside and outside of the H2 region, so just recap, inside the H2 region, number density up at 10 to the 10 per meter cubed, temperature 10 to the 4 Kelvin. Outside, it's mostly still molecular cloud. It'll have a pretty much similar density because remember all of this was one collapsing cloud at one point, but the temperature would be much, much lower, about 30 Kelvin. So you can see that the temperature is about 300 times higher. Also in here, you've got basically 4 times the number of particles, right? as you've got for molecular hydrogen, because you first of all dissociate your molecular hydrogen into 2 atoms, and then each atom gets ionized into a proton and electron, so that's 4 times the number of particles. So you've got another factor of 4 or so there. So, you know, basically the pressure inside the H2 region is about 1,000 times higher than its surroundings. So it's just going to want to expand because it's a higher pressure. So the high pressure gas will start to expand. And, you know, we can see that when we go and actually look at H2 regions on the sky. So early on, they will be quite compact and dense. And so if it's a small size, it will be quite a young H2 region. Obviously, we need to take into account how far away they are here, but if they're all in sort of in our galaxy, then this applies reasonably well. So here's some example sort of radio images, and this is a near-infrared image taken at around sort of 1 to 2 microns of the same object. Okay, so this is a classic what's called ultra compact H2 region. It's quite small, and you can see that you see the same structure here in the near-infrared and the radio. In the near-infrared, obviously, you see all the stars as well, which you see nothing of in the radio. So this image comes from the radio survey of the plane, the so-called Cornish survey that I've been in leading over the past years. If you went to further into the optical band, you would see absolutely nothing here. You would not see the nebula. And that's, again, the radio completely unaffected by dust extinction. But if you look at other objects, they are much bigger on the sky. So this one, it's only about 20 arc seconds across or something. This object here, which is M17 or the Omega Nebula, is much bigger. So this would be several arc minutes across on the sky. This is the radio image. Okay, here again, the near-infrared image. This one is now expanded up and become a lot less dense, and so you can see it in the optical as well. But again, it's severely affected by dust extinction here. So the clear view of this kind of shell of ionized gas is really seen most clearly in the radio. Okay. In the near-infrared, you spot that there's a whole cluster of stars in here ionizing this thing. So again, it's not a single star driving this anymore. You've got a whole bunch of hot stars in here. And you can see that actually looking at this, the gas is sort of flowing away in this direction. That's the expansion. It'll just break out and expand. And eventually, this will just blow most of this molecular cloud away. Okay. And then you're just left with your cluster of stars. In this optical image here, you can see all the bright blue stars. So they will be the hot massive stars that were, previously were ionizing all these H2 regions, which have now expanded up, and there's hardly any of the cloud left here, just a bit down here. Okay. So these are in terms of spectral type, if you want to use astronomers' notation, these are sort of O and B spectral type stars, the hot blue ones, and these are referred to as OB associations. Okay. So that's the kind of, endpoint. These are now basically just main sequence stars, not surrounded by any gas anymore in the field, and will just join the galactic population. So we've gone through that evolutionary sequence there. So before we move on, we'll just have another 5-minute break. Just thinking about what we were just talking about there. Obviously, to start with, gravity was dominant, and the whole molecular cloud was bound by gravity and collapsing in and formed this sort of cluster of stars. So that was bound by gravity. But now, once you end up with that, it's like an OB association, they're not even bound together by gravity anymore. The stars will just drift apart and disperse over time. So what's changed? Why was it bound by gravity initially, but now there doesn't seem to be enough mass in the star cluster to keep it together anymore, and it's dispersing? So just have a little think about that. over the break, and see you in 5 minutes.